Can you see my screen? Okay, I'll start. So let's put some. The main motivations used to justify the development of quantum computers is the belief that they have the ability to efficiently simulate many-body quantum systems, and that this will have applications to chemistry, medicine, materials design, and whatnot. But in this work, we ask a quite simpler question, which is to what extent can existing prototypes simulate quantum non-locality? And it turns out that we find that it's not an easy job. So I will try to explain what's going on here. So one of the key observations we do is that determining to what extent a given processor can simulate genuine multipartite non-locality can be useful for assessing whether it functions correctly or not. And therefore, it can be used as an important tool for users to decide whether to run their algorithms or not, as well as to determine which devices to use or choose. And it also has a benefit for quantum processors providers because it can also be used for calibration and benchmarking tasks. So where do we stand now? And why is this relevant? Nowadays, multiple vendors currently offer quantum processing units, both as commercial devices and cloud-based services. However, in the NISQ era, there are significant performance variations across different quantum processor prototypes. And these disparities persist even when you compare devices with identical architectures, for example, superconducting qubits or trapped ions, or even if you use replicas of the same QPU model, they will perform differently because they are noise is unique. A quantum processor is you can consider it as a complex system, and so they perform very differently. And also, the same physical device, when measured at different times during the day or during the week, it can display a very variable performance. And also, even inside the same processor at the same time, different qubit subsets will perform in a different way. So in the NISQ era, users and providers are forced to make choices. So, like, should I buy this device or not? Should I fix it or not? Should I hire this device or not? And more importantly, ideally, users will like to test quantum processor units before buying them or and without revealing their algorithm. So there should be a test layer before buying or hiring a service. And also, there is the problem of strength and benchmarking. Sellers are interested in showing how strong their devices are in terms of quantum resources. So our proposal is that we claim that tests based on genuine multi-party locality constitute a key tool for all these tasks, possibly in combination with other tests. I think that somebody has an open microphone. Uh, okay, I will go on, but there's somebody with microphones. Okay, so our test is based on ideas taken from fundamental physics, and it is a test as a whole. It is not restricted to single qubits or pairs of them, and it tests a given set of target qubits as a whole. Okay. And the method relies on establishing correlations between qubits across distinct and incompatible measurement contexts. As such, it functions as a test of quantum contextuality, leveraging non-Clifford resources in the process. So, Now I will try to explain the ideas behind the EPR argument and the development of Bell inequalities. So the EPR debate dates back to the 30s of the last century, and Einstein, Podolsky, and Rosen proposed a criterion for reality of for quantum systems. So they say that if without in any way disturbing a system, we can predict with certainty the value of physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So the typical setup is a source that emits two particles, and these particles are prepared in a special state in such a way that when you measure, for example, the position of the first particle, you will be able to predict the position of the second particle. And if you measure the momentum of the first particle, you will be able to predict with certainty the momentum of the second particle. And this can be achieved using entangled states. There is a similar version of the EPR example with spins, which is the one that we will use today. And it's the one which is, it's easier to explain perhaps because it uses finite dimensional quantum physics. But the idea is that EPR are using the principle of locality here because they say that since at the time of measurement, the two systems no longer interact, no real change can take place in the second system in consequence of anything that may be done to the first system. So suppose that you have two particles and these particles are created and prepared in an entangled state and they separate themselves and they can be possibly very far away. So in the first particle, you measure something, you do something there. So the principle of locality says that if you measure something on the first particle, it cannot affect the second particle instantaneously. So whatever you do on the first particle, it cannot alter the state of the second particle instantaneously because of the principle of locality. But the problem is that if you use an entangled state, for example, a single state, you will be able to predict the value of the spin of the second particle because they are correlated. So this is the typical entanglement paradox, if you want to call it that way. And given that if you assume the principle of locality, and if you are able to determine the state of the distant particle because of correlations, because they are correlated in an entangled state, then they conclude that the wave function is not specifying all elements of reality. So Einstein, Podolsky, and Rosen are forced to conclude that the quantum mechanical description of physical reality given by the wave function is not complete. Some decades later, Sean Bell joined this debate and started an investigation to see whether this debate could be tested empirically. So he says that since we can predict in advance the result of measuring any chosen component of the second spin of the second particle by previously measuring the same component of the first particle, it follows that the result of any such measurement must actually be predetermined. So he concludes, following Einstein, Podolsky, and Rosen, that there is an element of reality related to the spin of the second particle. And this can be done if you prepare particles in the singlet state. This can be done in all possible directions. So there should be a well-defined spin value for the second particle for every direction in space. So since the initial quantum mechanical quantum wave function does not determine the result of an individual measurement, this predetermination implies the possibility of a more complete specification of the state. he says, let this more complete specification be effected by means of parameters lambda. Lambda will be here called hidden variables. So these are parameters that we cannot access in the laboratory, we cannot control them, but notwithstanding, they are responsible for the things we observed and the correlations. So the crucial quantity here is the probability of observing the results A and B, given that the first experimenter and the second experimenter measure A and B bolded respectively, and given that the system is prepared in the hidden parameter lambda. Okay, so this is the fundamental quantity here, out of which correlations will be built and computed. So, as a review of what I am trying to say, each quantum observable, like each spin observable, in every possible direction has a determinate value, even before we try to measure it. And Sean Bell says measurement just reveals its value. Why this is so? Well, because of the principle of locality, given that we are able to predict what will be the value, the spin value of the distant particle, then it follows that there must be an element of reality attached to it. So the value, the value of spin of the distant particle should be predetermined. Now, the result of each experiment is predetermined by a hidden parameter, lambda. Or you can, more specifically, there exists a hidden variable which influences the result in a probabilistic way. And this is expressed by the probability distribution P, AB bolded, and lambda. Okay? So this is contained in this seminal Sean Bell paper and extracting from it. So, using this reasoning line, what you obtain is that the observed probabilities, this means that, let's say, the first party, Alice, measures bolded A, and the second party measures bolded B, and they obtain results A and B. So the probability of all these is governed by this formula, and this formula is built up of the following. We said before that the main quantity was this probability here, depending on the hidden parameter lambda. And now it comes the crucial assumption by Sean Bell, which is the assumption of locality. He says, given that nature is local, or if we assume locality, then this probability should be factorized in this way, in such a way that, for example, what Alice observes on its party will not depend on what Bob does on its party, and on the distant party, okay? So this is the principle of locality. Now, you could say that hidden variables means that you can write down probabilities in this way, that there are some hidden parameters that will allow you to have this quantity, depending on lambda. And the principle of locality says that probabilities should be factorized in this way. So this is, as a whole, this is called the local realism assumption or hypothesis, okay? And under the local realism assumption, you can write down the physical probabilities, the ones that you observe, that you can observe in the laboratory in this way as an integral. And the hidden parameter lambda is governed by its own probability distribution, which obeys the standard normalization of the probability distribution. And importantly, it will not depend on the measurement setup. So there is no dependence between the preparation of the source of the particles and what Alice and Bob choose to measure. So under all these assumptions, which can be termed local realism, then the probability can be written in this way. And using these probabilities, you can compute the mean values. You can compute the correlations between, for example, Alice choosing bolt A direction and Bob choosing bolt B, and then A and C and so on, and whatever correlations you want. And it turns out that under the local realism hypothesis, I mean, if you assume all of these, then an inequality follows. This is what Bell proved. But it turns out that if you compute these correlations according to quantum predictions, it turns out that the inequality is violated. And more importantly, this can be tested empirically, and the predictions, what was found in experiment is that the predictions of quantum theory seem to be correct. So for some reason, local realism is wrong. Then either assuming that there exists lambda is wrong, or the separability condition is wrong, or both are wrong. Okay, so but globally, local realism is wrong, and but it could be both. It could be, so we don't know, but what we know is that local realism seems to be wrong, and as I told you before, this can be empirically tested, and I put here the original Bell inequality, but nowadays there is a more popular version which is a Clausen-Horn Shimony-Holt non-locality inequality, which is pretty much the same idea as before. So if the correlations associated to a quantum state are lesser or are greater than 2, then they cannot be simulated using local realism. This is the message behind this inequality. But then in this talk, we will focus, well, this is the well-known quantum non-locality in its most popular version. But in this talk, we will focus on multipartite non-locality. So when there are more than 2 particles, the situation becomes more complicated, because you might have a state like in which 2 particles are fully entangled and display full non-local correlations, but the third particle is not correlated with the first 2. So you might have a situation like this, or you might have a situation in which everything is non-locally correlated with everything. So you need to distinguish between these kind of situations when you have more than 2 particles, and the problem becomes more and more complicated when you add more particles. But let's just focus on the 3 particles case for now, and here it comes the concept of genuine multipartite non-locality. Okay, so in order to distinguish a situation like this from a situation like this, let's speak a little bit about it. Suppose that you have a state in which the first 2 particles are entangled and following the single state correlations. It's the first 2 particles are prepared in the singlet state, but the third one is completely disentangled from the first 2. Okay, suppose in this situation, you say that the 3 particle system displays some kind of non-locality, but it is not genuine multipartite non-locality. Why? Because you can create a bipartition of the system in which the correlations between these 2 parts can be modeled using local realism. Okay, but then you want to distinguish this situation, the top situation, from the bottom situation in which you have something like the G8Z state. And this is, and here there exists no bipartition in which you can use local realism. Okay, so this was studied first by Svetlichny, and he derived what are now known as Svetlichny inequalities. And it's a family of inequalities that are tailored to test this. if you find a violation, if the correlations of the quantum state are such that you find a violation of these inequalities, then you say, or you are sure, and you can say that they display genuine tripartite non-locality. Okay, and notice that for computing this magnitude, you need to measure correlations in different measurement contexts. You need to select different spin orientations for the three particles, and you need to compute these correlation terms. And out of these correlation terms, you build this quantity. And if this quantity is greater than 4, you can conclude that the system displays genuine tripartite non-locality. And this can be generalized for n particles. And you can speak about genuine multipartite non-locality. A critical observation is that non-locality is not the same as entanglement. So this is a stronger test. So if you try to test whether a quantum system displays genuine multipartite non-locality, it will be harder in general than testing whether it is entangled or not, because entanglement and non-locality are not equivalent physical concepts. And there exist entangled states which admit local hidden variable models. Okay, this was first discovered by Werner in this seminal paper, but the situation becomes much more complicated when you have multiple particles. I will check on the WhatsApp whether everything is okay. Okay. Okay, but then the question is how to simulate genuine multipartite non-locality in a quantum computer. So what we try to do in our work is to implement this test, this non-locality test, in a quantum computer. This is the idea. So this is a schematic picture where the connectivity of an IQM processor is shown. So, for example, suppose that you choose qubits 1, 4, and 2, and then the idea is that you need to measure these correlation terms or make an implementation on a quantum computer of these correlation terms, and then you need to simulate the spin orientations, ABC, ABC primed. There are 2 spin orientations for each particle, displayed here as blue and yellow arrows, and you need to create in a quantum computer these correlation terms and compute the statistics. So what we do first is state preparation. We use some quantum gates which are applied to the set of qubits selected, and make a state preparation, and we call the state raw, and then we need to simulate local measurements. To simulate local measurements, you can use local spin rotations, just unitary operators applied to the spins, which simulate a measurement in a concrete direction, and then you measure in the computational basis. And out of this, you can compute the correlation terms that appear in the inequality. Remember that you need, in order to do this test, you need to compute these correlation terms. In the 3 particles case, there are 8 correlation terms, and we need to do the statistics for all of them. So what you need to create is the set of circuits. There will be, for each test, 8 circuits, each one representing a given correlation term. And out of this, you can just compute the let's call it Svetlitsky operator mean value, if you want to call it that way. You can compute this quantity and check whether it is greater than 4 or not. And then you can see up to which point your quantum processor is capable of simulating genuine multipartite non-locality. So this is the elementary block of our test or benchmark tool. And this is done with the research team at the University of Cagliari. And these are the team members. And the results that I will talk about today are contained in this paper, in this publication, which is currently under review. So now let's go back to a foundations of physics problem. So we spoke about the first foundations of physics problem, which is non-locality, but now let's talk a little bit about quantum advantage or quantum supremacy. So the story started perhaps with Feynman. There were others, but Feynman proposed that as nature is quantum mechanical, then if we want to simulate nature in an efficient way, we should use quantum computers. This is basically his idea. And it is based on the assumption that it is exponentially hard to simulate quantum systems of multiple particles, multiple components. And this is what we find in numerical simulations. It is very hard for supercomputers to simulate quantum systems of multiple components. And so the idea is that if you are able to build a strong enough quantum computer and which is not which can get rid of noise, so to say, so it admits error correction, you will be able to simulate quantum systems of multiple components in an efficient way. That's the idea. Okay, but simulation of big Hamiltonians is very promising because it has a lot of applications, but we ask for a simple questions here, which is, what about simulating genuine multipartite non-locality? This is relevant for technology. And all of this is related to the question, why do we believe that there is quantum supremacy or advantage? We study how genuine multipartite non-locality is distributed over the quantum state space using quantum random circuits. And this is also relevant for technology and for foundations of quantum physics. I will try to explain you why. And our work is related to the following questions. Why quantum dynamics seems to be essentially different from classical dynamics? And what is the essence of quantumness? Is quantum non-locality essential for quantum advantage? And how much of it and how? Is a quantum computer non-local? How can we be sure of that in the sense of loophole-free test? Because you can notice, if there are physicists in the room, you can notice that if you want to simulate non-locality here, then the first problem that you can observe is that the qubits are so close. So how are you going to grant that the no signal condition is being fulfilled? Because everything is so close. How can you grant that the measurements that you do are independent and separated, space-like separated? That's something that you cannot grant, I believe, in a quantum computer. But then this is the reason why I speak about simulation and not direct non-locality. I'm not saying that you are creating non-local correlations in a quantum computer, but that you are simulating non-local correlations. That's very important because in the end, at the end of the day, it will turn out that what we do here is a type of contextuality instead of non-locality. But I will speak about later if I have time. Okay, so you know that the main assumption of quantum computing is that the extended Church-Turing thesis is wrong, and we believe that a classical supercomputer will not be able to simulate efficiently what a quantum computer can do. But the question is, what is the reason of quantum advantage? So In order to find some clues to answer that question, what we do here is to study how quantum resources are distributed in the quantum state space. You know that the state space dimension of a quantum computer grows exponentially in the number of qubits. So you might wonder how the resources that a quantum computer can produce are distributed all along the quantum state space. Where are they? Are they concentrated in some specific regions? And it seems that also that the size is not the only important feature. Quantumness matters because it turns out that we believe at least that if you want to have some quantum advantage, you need to have some entanglement, some non-locality, some contextuality. But the problem is tricky. And it is also related, this discussion is also related to certification. You try to answer questions such as up to which point a given quantum device is able to generate the whole quantum state space, or how much of it is necessary for technological advantage. I will try to explain you that this is to a certain degree not known. There are many not known things. So if you don't know nothing about quantum random circuits, think about RAIN. RAIN, suppose that the quantum state space is represented by this circle here on the floor, and you have RAIN. So the idea of RAIN is that it falls homogeneously. It will not rain in some specific regions more than in others, but every region will receive essentially the same amount of water or droplets, so to say. So the idea is that if you throw quantum random circuits, what you are doing is choosing random points in the quantum state space, but in a uniform way. You are not being biased to any specific region of the quantum state space, but you are doing like a sort of rain. You are choosing points in a random way and in a fair way. So this is the idea. So using quantum random circuits, you can explore the quantum state space because you can see how things are distributed. Because once that you have chosen a big enough set of points using quantum random circuits, then you can see which states have certain properties and which states don't have certain properties. And by doing that, you can compute relative volumes. You can, for example, if this were just a circle on the floor and this were just rain droplets, you will be able to estimate the relative volume of these two parts just by counting the droplets. So by doing this, you can explore the properties of the quantum state space. So the idea is that on each layer of a quantum random circuit, you choose random, you make a random choice of gates, and this will create a random states. And if you do it okay, you will have a unitary or approximation of a unitary matrix distributed according to the Haar measure, which is the uniform probability distribution for unitary operators. So what we do is to produce hundreds of thousands of copies, or well, depending on the numerical experiments, we do a lot of copies of quantum random circuits, and for each quantum random circuit, we compute the maximal degree of violation of the Svetlichin inequality. And out of this, we build an histogram. On the right, you have an histogram computed using produced using random circuits that take gates from the Clifford plus T set. And on the right, you have a simulation of Haar distributed unitaries using the library CP. And so using different methods, we compute these histograms and we obtain essentially the same results, proving that our method for producing quantum random circuits works okay, at least for 3 qubits. This is important. And what is important here is that the Clifford plus T set is complete and universal. So this means that out of this set, you can simulate any possible unitary that you can imagine. And we will compare these histograms with the histograms produced with a non-universal set. So we can do this for 3 qubits, 4 qubits, 4 qubits, and see how the histogram's shape changes as the number of qubits grows. And we can compute also the fraction of states that violate the non-locality inequality. This is important because for 2 qubits, we have that most states produced do violate Bell or Clausen-Horn-Shimony-Hall inequality, but then for 3 qubits, the fraction is 78%, but then for 4 and 5 qubits, the violation fraction drops off very fast. This is the violation fraction of the Spetlichny inequality as the number of qubits grows. This means that the relative volume of the set of states violating this particular inequality drops to 0 when the number of qubits grows. Notice that if we don't use Spetlichny inequality, which is a genuine multipartite non-locality inequality, and we use Mermin inequality instead, then the fraction will not go to 0. And this is interesting because Mermin inequality will be sensitive to plain non-locality, in the sense that if a state violates Mermin inequality, then you're sure that it will not obey local realism. But you cannot discard using Mermin a situation in which some bipartition can be described using local realism. So Mermin inequality discards full local realism, but will not discard the hybrid versions of local realism. So it is interesting because at least with regard to these particular inequalities studied here, we find that the volume of the set of states violating them drops to 0 for the case of genuine multipartite non-locality. But then this leads us to the question, what is the relative volume of the set of genuine multipartite non-local states? And it is important to have in mind that the fact that for a given state, the Spetlichny inequality is not violated will not preclude, in principle, the existence of other non-locality inequalities to be tested. So we cannot conclude that the volume is essentially 0. So this challenge is not obvious. But it is interesting to use this methodology to study the relative volume of the set of genuine multipartite non-localities, non-local states. And what is interesting for technology about these histograms is that in pink here, I'm showing the ideal histogram, okay, on the back. But when you start to increase the noise of the system, then, of course, the simulation will be deteriorated by noise because there will be imperfections. And then the histogram moves to the left until no non-locality is observed, okay? And this is very important because by comparing the noisy histogram with the ideal one, you can have a very concrete idea of the noise affecting your system. So this can be used as a benchmarking tool or for calibration purposes on a quantum processor. Another important thing is to use only Clifford circuits. If you use only Clifford circuits and you compute the histograms of violation, instead of obtaining a continuous range of values like the ones that we get here, you obtain a somewhat discrete peaks. You obtain that the maximal violation degree of the Spetlichny inequality for only Clifford circuits or states prepared using only Clifford circuits is concentrated in some very specific values. And what is interesting is that you can obtain maximal non-locality violation, but you cannot obtain all possible values of violation. The violation values are concentrated in some particular points. We don't know why this occurs, but what we know that is that Clifford circuits are efficiently simulable using a classical probabilistic Turing machine. And so we think that these plots give a possible clue for understanding quantum advantage, because you know that by Gottesman-Neal theorem, non-locality cannot be enough for explaining quantum advantage. Why? Well, because using Clifford circuits, you can prepare states displaying maximal non-locality, because the sheared set states can be prepared using only Clifford resources. But what we find is that the difference between a universal gate set and a non-universal and classically simulable gate set is that the distribution of the resource is very different. The distribution of non-locality in the classically simulable set is picked and centered in some specific points of the quantum state space. Of course, this is not so surprising because the set of states that you can produce using Clifford resources is finite, and it seems that they are concentrated in some specific regions of the quantum state space. But what you find when but the discreteness of this plot is, at least for me, intriguing, because there is no reason in principle that they are so concentrated in these specific points. So then, okay, I will go on with the how can this be used for technology, right? I don't know how I am doing with time. I guess I took more time, but let me go on a little bit with this, because what we do here is to use AWS Bracket to access different quantum processing unities. More specifically, we used a quantum computer from IonQ and a quantum computer from IQM to test these histograms, to make a sort of implementation of the histograms that I showed you before, and try to see how they perform, right? So in this plot here, what you see is not the full histogram that I showed you before, but what we did is to choose different selected states. We produced a lot of quantum random circuits, and out of this set, we choose some specific representative states, and we did the Spectration 10 test on them, and we repeated each experiment, in this case 10 times. And in this plot, what you can see is that the black crosses here are the ideal results. So should the quantum computer were perfect, you should obtain these black crosses on top. But given that it is not perfect, what you obtain is these points here. And you see that there is, of course, a dispersion, because each time you repeat an expectation test, you obtain a slightly different value. And this difference can give you an idea of noise also. So by comparing ideal with the experimentally tested one, we obtain a sort of first sample of how the quantum computer is working. Why I speak about fair sample? Well, because we use quantum random circuits, and by doing that, we somehow forget about the architecture, because we are using the best states that the quantum computer can produce, because we get rid of any optimization procedure related to the fact that you need to represent a given state in terms of NAT gates and so on. So this is the idea. We are trying to get a first sample of the quantum state space of these 3 qubits of this quantum computer. And you can do the same and compare different quantum processors. Here we have the results for IonQ and IQM. We use Area 1 and Garnet, respectively. And as you can see, I would say that they perform quite similarly. Naturally, IonQ is on top because it's a technology limitation. Ion trap quantum computers perform better than superconducting qubits quantum computer in general. But for 3 qubits, they behave similarly, I would say. But what is interesting is that when we try to do the same by augmenting the number of qubits, we were not able to find violation of the 4 qubits spectration inequality using shared set states for IQM. And this was even worse for 5 qubits. But we could find, or we were able to simulate a genuine multipartite non-locality of 5 qubits with the IonQ machine. This is interesting because it allows you to compare different technologies. And you could use these points here, the ideal points, as a figure of merit, like saying, oh, okay, this is the north where I should go. If I want to improve my quantum computer in the future, I should be able to simulate 5 qubits, for example, genuine multipartite non-locality inequality. So, using quantum random circuits and the simulation of the spectration inequality, one can evaluate the performance of quantum processors, and it is a test based on fundamental physics that evaluates the device as a whole. But it could not be the device, just a family of qubits. And one can focus on target qubits for calibration goals. And so one of the messages here is that even a small number of qubits, even performing these tests on a small number of qubits, gives relevant information about how the computer is working. And what we did is to compare the results obtained with quantum circuits using only Clifford gates, which is a non-universal and classically simulable set, with regard to those that use Clifford plus T gates, which has magic and it is universal. The main difference that we find is that for the former, the violation degrees obtained are concentrated in certain specific values compatible with the discrete nature of stabilizer states. And what we are working now is on a collaboration with the team of the Leibniz Rechenzentrum in Germany, in Munich, to use and improve this non-locality benchmark tool. And we use it to test quantum processors that are installed in the Leibniz Rechenzentrum. And what we do is we access through the Munich Quantum Valley API, we can access the quantum processors mounted in the tomb, and we compare an IQM machine with an Alpine Quantum Technologies machine. Okay, and so our goal is to develop theoretical tools and useful software for testing quantum computers. And the software should be such that it is easy to use, it works plug and play, and it's easy for end users. So this is our idea. So if you want references for the research presented in this talk, well, the non-locality test is published here in this paper. I hope it is published soon. And if you want to learn more about contextuality, I didn't talk much about contextuality in this talk, but let me tell you, this is all related to contextuality. You can have a look at this paper where we exploit a measured theoretic approach to negative probabilities and give a similar discussion to the one we present here. And if you are interested in the philosophical aspect of this discussion, please have a look at this paper where I discuss how quantum technologies are related to the non-Kolmogorovian structure of the quantum state space. So this is all. I hope you have enjoyed the talk, and I'm open for questions now if you're interested. Looks like people were. Are you there?
Oh, my mic was closed, so I'll talk again. Now we'll open the floor for questions. If you have any questions to make for Dr. Holik, please feel free to ask. Just write it in the chat. And once again, thank you, Fed, for accepting the invitation. It was a pleasure to hosting this lecture for you.
No, no. Thanks to you. Thanks to you. Thanks for giving me the opportunity to share my research here.
It was great. Uh, I'm thrilled to host this lecture, and it seems we don't have any questions from the audience right now, but I can send to you later if someone reach me. Make it if someone makes any questions to me, I can pass them to Dr. Holik. So thank you for the lecture, and for everyone watching, stay tuned for our next session. And until then, take care and see you soon. Goodbye.
Okay.